The history of aviation is often written in the wreckage of machines that failed to return to Earth. But there is a specific category of loss where the aircraft does not fall from the sky, but rather flies directly into the surface under full control. On July 21, 1948, a Boeing B-29 Superfortress was operating over the border of Nevada and Arizona. It was not carrying a nuclear payload or a rack of incendiary bombs. Instead, it carried a prototype high-altitude sensor, an experimental sun tracker meant to explore sun-based navigation that could later support long-range guidance. The aircraft was serial number 4521847, a modified F-13 reconnaissance variant stripped of its defensive turrets and gunnery stations to save weight and increase range. In place of weaponry, the upper fuselage was fitted with a specialized observation blister housing the sun tracker, the centerpiece of a sensitive, high-priority effort known as the Upper Atmospheric Air Research Program, sometimes referenced as Project 288. The objective was to develop a guidance system that could navigate automatically by calculating the angle of the sun, independent of ground-based radio signals or human input. For the United States Air Force, it was the key to delivering weapons across oceans without relying on a pilot to find the target, and proving it would demand extremes. To calibrate this delicate instrument, the mission profile required extreme contrasts. The engineering team needed data from the edge of the troposphere and data from the surface of the Earth. The flight plan called for a run around 30,000 to 35,000 feet, followed by a rapid descent to as low as possible for a low-level pass. The location selected for this calibration was Lake Mead near the Overton Arm. Open water, uncluttered, a flat sheet of reservoir where the crew could fly a controlled low pass with nothing in the way. The crew on board consisted of 5 men, commanded by Captain Robert Madison. They were operating in a unique environment. The B-29 was among the first mass-produced bombers built around fully pressurized crew compartments, an attempt to reduce fatigue on long, high-altitude flights. But comfort does not change what happens when altitude disappears. In a ditching, survival is decided by seconds, clear procedures, and a clean escape route. The high-altitude portion of the mission was completed successfully. The sensors tracked the sun, the data was recorded, and the aircraft performed as expected. Captain Madison then initiated the descent toward the Overton arm of the lake. The plan was to level the aircraft just above the water surface to test the sensor against the atmospheric density and heat shimmer of the desert floor. Flying a 99-foot-long bomber with a wingspan of 141 feet at low altitude is a task that demands absolute discipline. The B-29 is a heavy, momentum-driven machine. It does not react instantly to control inputs. At low altitudes, the margin for error is measured in seconds. The 4 Wright R3350 engines generated nearly 9,000 horsepower, pulling the airframe through the air with immense force. In this flight regime, the pilot must balance the lift generated by the massive wings against the drag of the dense air, all while maintaining a precise height above the terrain. That July morning offered no warning signs. The sky was clear, and the visibility was unlimited. There was no mechanical distress and no indication of system failure. The aircraft was functioning exactly as designed. The crew was experienced and the objective was routine. However, the mission profile introduced a hazard that was not marked on any chart. By forcing the aircraft to operate at the very bottom of its performance envelope, the sun tracker schedule removed the safety buffer of altitude. As the Superfortress leveled off over the water, the technical requirements of the sensor package collided with the limitations of human perception. The mission demanded a stable, flat trajectory. The lake offered a perfect horizontal reference, but the relationship between the aircraft and the surface was about to be distorted by the environment itself. The crew believed they were flying a precision test run. In reality, they were entering a geometric trap where their senses would betray them. By the time the crew needed an exact height, the numbers could be misleading. In the accident record, the altimeter was noted as incorrectly adjusted for local pressure. Over mirror-like water, even a small setting error becomes a big one. Near the surface, Captain Madison could not trust a single needle. He had to trust what he saw, exactly when the environment was about to lie. On the morning of the accident, Lake Mead presented a specific environmental condition known to aviators as the glassy-water phenomenon. The wind was calm and the surface of the reservoir was perfectly flat. Without ripples, waves, or floating debris, water loses its visual texture. It becomes a perfect mirror, reflecting the canyon walls and the sky above without distortion. For a pilot judging altitude visually, this condition is critical. The human brain calculates distance and depth by processing the motion of texture across the retina. When the surface is featureless and reflective, that data stream is cut. The optical feedback loop fails. In that moment, altitude becomes guesswork. Depth perception is severely degraded, and the slightest misread can put metal into water. The reflection of the terrain looks exactly like the terrain itself. Captain Madison was not flying into a void. He was flying into an illusion where the horizon line dissolved. The B-29 descended toward the Overton Arm at 230 miles per hour. The crew believed they were establishing a level flight path at a safe altitude. The physics of the situation dictated otherwise. The aircraft was in a shallow, powered descent. All four propellers were still driving hard, the fuselage heavy with momentum. The first point of contact was not the fuselage, but the propellers themselves. At that speed, water does not behave like a fluid that can be easily displaced. It reacts with the density of a solid. When the propeller tips struck the surface, the hydrodynamic drag was instantaneous and catastrophic. The sudden resistance exceeded the structural limits of the engine mounts. The violence of this deceleration triggered a sequence of mechanical failures that paradoxically helped the crew survive. The impact tore away 3 of the 4 engines, everything but the outboard port engine, shedding weight and bleeding off speed in an instant. That unplanned mass loss did 2 things. It reduced the load the airframe had to carry, and it dumped forward energy that might otherwise have been driven straight into the crew compartment. The fuselage, now lighter and stripped of its worst drag sources, performed something close to a skip ditching. The smooth belly planed across the mirror-like surface, leapt briefly back into the air, and then settled again, skipping for roughly a quarter mile before the bomber finally slowed. The one remaining engine flared and burned as the aircraft decelerated, then died as water and lost airflow took over. The interior of the aircraft remained intact. The pressurized crew compartments held their shape against the impact forces. The nose section, usually the most vulnerable point in a bomber crash, took the worst of the impact, crushing and opening the forward greenhouse rather than neatly surviving intact. Inside, the crew found themselves floating on a quiet lake. The violence was over in seconds. With the aircraft momentarily afloat, the crew deployed life rafts and evacuated rapidly. The B-29 floated for a short duration before the integrity of the fuselage gave way to the water intake. The damage to the tail section and the open engine mounts allowed the lake to flood the interior. The nose dipped forward, the tail rose. The aircraft slipped beneath the surface, descending into the darkness of the channel. It did not break apart on the way down. It glided to the bottom and came to rest, vanishing from the surface record for 53 years. For decades, the bomber's fate hovered between rumor, partial memory, and an imprecise patch of water. The lake had swallowed the evidence within minutes, and repeated interest over the years never produced a publicly verified set of coordinates. It was not until the turn of the 21st century that search tools finally matched the depth and scale of the loss. In the early 2000s, a team of local technical divers began a systematic search for the missing bomber. In 2001, a side-scan sonar search finally produced a return that looked like a bomber, and the coordinates were kept close at first. Optics and cameras were useless in the low visibility of a silted lakebed, so they relied on sound. A towfish flown just above the bottom emitted fan-shaped pulses of high-frequency acoustic energy to both sides. Soft mud absorbed the signal into darkness. Hard metal threw it back bright. And behind any solid object the sound could not reach, leaving a distinct acoustic shadow. Measure the length and shape of that shadow, and you can read the height and profile of the target without ever getting wet. The search team combed the grid for months. The target they were hunting was substantial, but the underwater terrain of Lake Mead is rugged, filled with submerged cliffs and rocky outcrops that can mimic the signature of a wreck. Finally, the sonar painted a return that was too geometric to be geology. The image showed a long, cylindrical shape with the distinct cross of a wing structure. The acoustic shadow revealed the high vertical stabilizer of a Boeing superfortress, standing proud of the silt. At the time the wreck was confirmed, the site lay deep enough to be beyond ordinary recreational diving. Down there, the water was cold and light was scarce, and the environment was unusually stable. Those conditions were harsh for humans, but helpful for preservation. Fresh water slows some forms of decay compared with salt water, and limited light reduces the growth that can quickly blanket exposed metal. When the first technical divers descended to the site to verify the target, they found the B-29 sitting upright on the bottom. The 3 engines torn away in 1948 were missing, leaving exposed structure on the wings. And the most striking evidence of the low-energy arrival was the forward fuselage, where the nose section showed clear damage from the surface impact. The iconic greenhouse cockpit of the B-29 is a complex lattice of magnesium frames and glass panels. In a high-speed impact, this structure is usually the first to disintegrate. At the bottom of Lake Mead, the divers found the glass intact. Through the windows, they could shine their lights into the flight deck and see the control yokes, the throttle quadrant, and the instrument panels. The flight engineer station was preserved as it was when the crew abandoned ship. The verification of the wreck confirmed the identity of the aircraft as the modified F-13 observation platform. The unique blisters for the tracking equipment were visible on the fuselage, matching the historical configuration of the Sun Tracker project. The survey had succeeded in locating the physical remains of the mission. However, finding the aircraft created a new operational problem. The site was no longer a lost rumor. It was a tangible asset sitting on federal land. The discovery did not mark the end of the story, but the beginning of a battle over who had the right to disturb it. The discovery of the B-29 in the early 2000s triggered a conflict that had nothing to do with aerodynamics or crash physics. It was a collision of legal definitions. A private group argued that decades underwater amounted to abandonment and attempted to assert salvage rights. The United States government countered that military aircraft remained federal property unless formally disposed of, and that the bomber lay within a national recreation area managed by the National Park Service. In August of 2003, a United States District Court judge rejected the private attempt to claim ownership of the submerged bomber. The message was clear. This was not a prize to be hauled up and sold. It was a federal cultural resource to be managed, documented, and protected. With the legal question settled, the National Park Service had to make an engineering decision. The structural integrity of an aluminum airframe that has been submerged for half a century is an unknown variable. The corrosion of the rivets, the fatigue of the spars, and the waterlogged condition of the interior meant that any attempt to lift the 99-foot fuselage would carry immense risk. The stress of a recovery operation could cause the aircraft to break apart, destroying the very history the court had just protected. The agency chose a strategy known as in situ preservation. This concept dictates that the most stable environment for a submerged archaeological site is the one it has already adapted to. Instead of removing the object, the resource is managed where it lies. The surrounding water, sediment, and pressure become part of the containment system. The goal changes from acquisition to documentation. The site becomes a laboratory where the processes of degradation can be studied over time, rather than a quarry for museum pieces. This decision meant the B-29 would not be raised. Access was managed in phases, periods of closure for assessment, and in some years tightly controlled, guided diving under strict rules designed to keep hands off the aircraft. For a time, it seemed the bomber was safe. But in situ, preservation depends on one thing the courts cannot control: a stable environment. And the lake itself was about to change the parameters of the site. The protection of the B-29 relied on the stability of the water column above it. When the aircraft was discovered, it sat at a depth of 280 feet. This placed it in the aphotic zone, a region of total darkness where photosynthesis is impossible. The lack of light prevented the growth of algae and aquatic plants that would otherwise colonize the aluminum skin. The pressure and the low temperature acted as a natural preservative, slowing the chemical reactions of corrosion. The isolation was absolute. However, Lake Mead is not a natural geological formation. It is a reservoir, an engineered system designed to store water for the American Southwest. Its capacity is defined by the height of the Hoover Dam and the inflow from the Colorado River. In the years following the legal ruling of 2003, a severe and prolonged regional drought began to drain the basin. The water level did not fluctuate normally, it entered a sustained decline. The surface of the lake dropped steadily, changing the geometry of the shoreline and the physics of the water covering the bomber. As drought drew the lake down, the depth over the wreck shrank dramatically. The bomber rose into the sunlit layer, where chemistry and biology move faster. The introduction of light and warmth to the crash site fundamentally altered the preservation equation. In the photic zone, the environment is dynamic. Light allows algae to bloom on the metal surfaces, creating a biofilm that can trap chemicals against the skin of the aircraft. The water at this depth is warmer and richer in dissolved oxygen, two factors that accelerate the electrochemical process of oxidation. The stable, inert tomb of the deep channel was replaced by a biologically active environment. The aluminum, which had survived the impact and 50 years of silence, was now exposed to the cycle of life and decay. The lowering of the water level introduced a second variable, human accessibility. At greater depths, the site was accessible only to a small number of expert technical divers with specialized training, planning, and support. The operational risk of such a dive naturally limited the number of visitors to a handful of experts per year. By the time it reached 110 feet, the wreck fell within the range of advanced recreational diving. The physical barrier to entry dropped along with the waterline. The National Park Service faced a trade-off. They could not refill the lake, and they could not move the aircraft without risking structural collapse. To manage this new reality, the agency shifted its strategy from secrecy to managed access. They established a controlled heritage diving program. Licensed commercial operators were permitted to guide divers to the aircraft under strict protocols. The B-29 became a monitored exhibit. The increased traffic brought regular visual inspections, allowing the agency to track changes in the airframe month by month. But the transition to the photic zone brought a threat that no permit system could regulate. As the light reached the fuselage, a biological invader followed the current. The most significant threat to the structural integrity of the B-29 did not come from the violence of the skip ditching in 1948. On January 6, 2007, quagga mussels were detected in Lake Mead, an invasive freshwater mollusk that breeds rapidly and attaches itself to any hard substrate in the water column. In a lake bottom dominated by silt and mud, the 99-foot aluminum fuselage of the bomber acted as a massive artificial reef. Within a few years of their arrival, mussels began coating large portions of the aircraft. They encrusted the wings, the stabilizers, and the frames around the cockpit, turning the bomber into an unintended reef. This biofouling created a new engineering problem for resource managers. Dense encrustation adds significant static load and can hold moisture against metal surfaces, encouraging localized corrosion through oxygen gradients and trapped debris. Details that were once crisp to survey teams, rivets, seams, and panel lines, can disappear beneath a living crust. For the resource managers, there is no viable solution to remove them. Mechanical cleaning would require scraping the aluminum, which would strip away the protective oxide layer and cause more damage than the mussels themselves. Chemical treatments are impossible in a public water reservoir. The decision was made to accept the biofouling as a permanent condition of the site. The B-29 is no longer just an artifact of the Cold War. It has become a biological host. This transformation defines the current mission of the site. The aircraft is no longer being studied solely for its history as a sun tracker platform. It has become a submerged laboratory for materials science. By monitoring the corrosion rates of the B-29 against the growth of the mussel colony, researchers gain data on how historic metals degrade in freshwater environments. This knowledge is applied to the management of other submerged cultural resources across the United States, from shipwrecks to flooded infrastructure. The legal custody of the wreck remains absolute. The United States government retains ownership in perpetuity. The site is a protected landmark, listed on the National Register of Historic Places in 2011. While the drought continues to fluctuate the depth and the mussels continue to colonize the structure, the aircraft is secure from commercial salvage. The survival of the crew in 1948 was a matter of pilot skill and hydrostatic luck. The survival of the airframe in the 21st century is a matter of federal law and disciplined stewardship. The B-29 of Lake Mead began its final flight with a mission to track the sun for the guidance of missiles. it failed to complete that calibration. Instead, it succeeded in a different, longer duration mission. It serves as a benchmark for preservation in a changing environment, holding its station in the darkness of the Overton Arm, proving that even a lost machine can continue to generate data long after its engines have stopped.